We're going to talk about disjoint sets first. But actually, we're going to solve the PPP exercise. This is where we left in the last class. So the problem was finding the earliest time when all the members get to know each other, or at least they are in the same social network. Okay, and the first thing we need to do is sorting these time steps. We want to check the earliest time step. So we are going to first sort these logs with timestamp. So we are going to use this key and lambda x 0. So this one is the key means we are going to sort the items inside these logs according to this criteria. And the criteria is going to be the first element, because the first element is the timestamp. And because we have 3 items inside each index, this sort algorithm does not know what to choose as a criteria for sorting. And we're just passing this parameter key and signify that the first element among these 3 items is going to be the criteria. So timestamp is going to be the criteria for sorting. And next, we're going to create a disjoint set. And because we have n number of people, we're going to make n disjoint sets. And we're going to count the number of groups. And initially, it's going to be n. Okay, so first, we're going to separately make disjoint sets for each person. And what we are going to do is, for each timestamp, we're going to have 2 people, friend A and friend B. And we can retrieve these 3 numbers or these 3 information from logs. So this one signifies the timestamp and the index of the first friend and the index of the second friend. And what we are going to do is, if these 2 friends are not connected in some way, what we are going to do is union these 2 friends. And then we're going to decrease the number of group count. And after we did this, if the number of group count becomes 1, that means we have just 1 group of people, meaning that all the people inside these logs are connected in some way. Then we just need to return the timestamp, because this is the earliest time when all the people get to know each other. And after we checked all the information inside these logs, and we have not reached the group count of 1, that means everyone cannot be connected. So we are going to just return -1. So this is the one solution, and there might be other solutions. So if you can pass all these test cases, then your solutions are also okay. Any questions about this problem? Okay, let's move on. So from now on, we are going to talk about graph traversals. What is graph traversals? Graph traveling means visiting all vertices inside a graph. And we do not visit the same node again. So for all nodes, we're going to visit each of them just once, no more than twice. And there are two major methods to visit all vertices in a graph. And the first one is called depth first search. And the second one is called breadth first search, and abbreviated as DFS and BFS. In fact, we talked about these two algorithms when we were talking about stacks and queues. What is the difference between DFS and BFS? In fact, we saw these when we were discussing stacks and queues. And this is the illustration of DFS and BFS. So what we are doing is we first start from this node and go to as far as we can go. So we go as far as we can go, and we reach the end and come back and start visiting other nodes again. So it looks like the roots of some plant. However, in the case of BFS, we're just increasing the coverage one by one, like this. So we are increasing the coverage one by one, like this. So the configuration of DFS and BFS looks quite different. So it goes like this. However, BFS goes like this. So in Korean, it is called 응고선. I don't know how to call this in English, but anyway, these are how we perform DFS and BFS. Okay, let's implement DFS and BFS because we talked about it, talked about these two concepts in stacks and queues. So I guess we can implement these two concepts right away. All right. So from now on, we're going to talk about graph traversals. And the first thing we're going to talk about is DFS. By the way, I'll just show you some pseudocode, and you are going to implement the actual DFS and BFS solving PPP exercises. Okay. So first, we can implement DFS using recursion. So let's say we have G and V. Here, G signifies a graph, and V signifies the starting vertex. And let's say GV this one returns adjacent vertices of V. Okay, then how can you implement this one? First of all, we are going to check this vertex V is visited. So we are going to input feed true to visited V. And originally we need to have another list. This one is false times n. So we're going to check whether we visited this node or not. So these are some assumptions before we implement DFS using recursion. And after we mark that we visited this node V, starting node, what we are going to do is do something useful. So this means for each node, you need to do something like doubling the value of the node or getting the value of the node, things like that. To do whatever you want to do after you come to this node V. And after that, what we are going to do is for each neighbor in GV, so from our assumption, this returns the adjacent vertices of V. And for each node, each neighbor that is not visited, what we are going to do is call recursion of the DFS like this. So this is basically how we implement the DFS using recursion. So pretty simple. However, sometimes we do not prefer recursion because that could cause Stack Overflow errors. And another way of implementing DFS is iteration. And for implementing DFS using iteration, we need to use a stack. So here, stack is just provided. And what we are going to do is we first initialize the stack with the starting vertex. And while the stack is not empty, what we are going to do is, let's say node. We're going to get one item from the stack. And if this node is not visited, that means we need to process this node. And to visit it, we're going to append this node n, and we're going to visit n. Let's say we need to have visited like this. So this is another way of implementing visited. In the previous case, we just initialize all the nodes as false. However, in this case, we're starting from an empty node, empty list, and increasing this visited node as we visit other nodes. Okay. And then what we're going to do is to the stack, we're going to add the neighbor of this node B, except the visited node. So this is another way of implementing DFS using iteration. Okay, that was DFS. And from now on, we're going to talk about BFS. So because in the case of DFS, we're going as far as we can go using recursion. We end up visiting the node at the end, and then move to the next step and find the end from this node and reach 6, and then go back and search another endpoint. So this is why DFS is implemented in this way, using recursion or iteration. On the other hand, BFS is somewhat different. In the case of BFS, we are going to use Q to implement BFS. So here, Q is Q and V is starting vertex. And what we are going to do is, first we are going to append V to our Q. And we're going to mark the starting vertex V as true because we visited. And we're going to visit V like this. And while our Q is not empty, what we are going to do is pop first element from Q. And for each neighbor in GV, if we have not visited this node, then we're going to append this node to our Q. And we're going to mark that W is visited. And then we're going to visit W like this. However, you don't have to visit W here. You can visit. You don't have to visit V here. You can visit here. So it doesn't really matter where you put visit. Okay, it's up to you. It's the different styles. And you can choose where to put visit. And another thing is you can also mark the visited status here rather than here. So it is up to you where to put visited or visit. All right. So that was BFS. And we use stacks to implement DFS. However, we use Q to implement BFS. Okay. So that was about BFS and DFS. And I'm going to give you one PPP exercise. And this PPP exercise, I'll also give you the full description of this problem. So this problem is about whether there is a valid path or not. So the valid path from source to destination. In this case, let's have a look at this first example. N signifies the number of vertices. So we have 6 vertices, and these edges signify the connection between 2 nodes. So 0 and 1 have 1 edge, and between 0 and 2 we have edge. And this source means the starting point, and destination is the end point. So we want to find whether there is a path we can reach starting from source to destination. If there is no valid path, no connection, then we're going to return false. Otherwise, we're going to return true. Okay? So these edges and N represent a graph. And what we want to do is check whether there is a valid path between source and destination in this graph. Take some time and try to implement this function.